Okay. Good morning, everyone. Let's get started. So first of all, we have released the Kaggle computation task. Well, if you can take a look at the canvas, there's a link put on the announcement, right? So click into the link, and you can join that in-class Kaggle computation. But of course, if you want to submit anything, you need to first have a Kaggle account, right? So, I mean, you have a few days or 1 week to play around that and then make a decision if you want to join this competitive project or you want to do some research project, right? So we'll soon release another assignment, which is called Project Choice. You're gonna submit a PDF, which tells us like which project you want to join. If you want to join the Kaggle project, so just let us know your UID and your Kaggle username so that our TAs can track. Right? If you want to do the research project, also please let us know. Okay. The second thing is about homework 1. So again, please start working on that. You can definitely work on that right now, right? Actually, after today's lecture, there shouldn't be any missing topic which is necessary to complete your homework 1, right? So you should be able to finish your homework 1 with after we have discussed in this lecture. Okay, so in the last lecture, we talked about ID3 algorithm, right? The most popular and classical decision tree learning algorithm, right? So we know that ID3 algorithm essentially fulfills a greedy heuristics to construct the tree to be as small as possible, right? So remember, our original goal is to construct a tree to represent data set, and such tree should be as small as possible. We view that smaller trees as the better choice. Why? Because we respect the so-called Occam's razor principle. And so we have some brief introduction about Occam's razor principle, but it's just kind of a philosophical principle saying that if you have a bunch of models can equally well fit the data, and if I want to choose the model, right, or I want to rank the model, we can always pick up the simplest one, or smaller size models. This has shown to be effective for many scientific and engineering problems, right? So in the decision tree learning, we kind of follow the same principle, right? We want to construct a tree to be as small as possible to represent data set. Right? But the problem is that if you want to find a globally minimum tree, that is very expensive, right? Imagine you got n features, right? And strictly speaking, you have to enumerate all permutation of those attributes and test, okay, if I follow this permutation to split the data set hierarchically, what's the tree size, right? And then I need to look at another permutation and follow the corresponding order split data set and see what is going on there, right? That would be very expensive, and it's going to be an NP-hard problem. So that's why in the practice we have to compromise on the efficiency, right? So that's why we're gonna choose a greedy approach, right? So greedy approach, I believe everyone knows the basic idea, right? We're gonna give up the global optimal stuff, right? Every time we just seek for a local optimal thing, right? But in that way, we can avoid backtracking the previous status, right? So every time I just find out the optimal solution given all the previous decisions, right? For example, you know, ID3 algorithm, right? At the beginning, I'm going to pick up attribute which currently can best split the data set, right? And then given that attributes has been applied, I'm not gonna change that attribute anymore, right? I'm gonna find out from the remaining attribute set which one is best to further improve the label purity and so on. Because every step we're trying to find out an attribute which can best improve the label purity. We expect that not after many steps. We're gonna make every subsets to be uniquely labeled, and our tree can stop the growth. Right? That's the basic idea. Right? And then we have a recursive algorithm procedure to conduct such a greedy tree growing procedure. Right? So I'll first give some outline of today's discussion, right? And then we're gonna have some more detailed review of the ID3 algorithm, because this is really, really important. I would rather like spend a little bit more time talking about its details, right? So today we're going to talk about some extensions of decision trees. Right? So we're going to talk about several variants of decision trees to address a few problems, like how do you handle as we discussed in last lecture, right? We use information gain to measure after you use one attribute to split on the data sets, what's the improvement of the purity, right? But information gain is not the only choice, right? We actually have a variety of metrics that can measure the purity, right? So we're going to talk about two other variants. One is called majority error. The other is called Gini index. Right? And then we're going to talk about what if your data set is not perfect, meaning that your examples might have some missing feature values. Right? Okay, because this is pretty common in practice. So we're going to talk about several strategies. Right? The most offensive strategy will break the example with some missing feature into fractional examples and plug them back into the whole data set, then compute information gain and so on. Right? It's a little bit complicated, but it's a very nice strategy. That's our main focus. Right? Then we're going to talk about non-Bloom features. Right? We'll see that if your feature or attribute is categorical, even it's categorical, sometimes it might make the tree too big. For example, if your feature is brand, like you might have 1,000 brands. That means if you use the attribute brand to partition the data set, you're gonna grow 1,000 branches in parallel, right? That's not something we want, right? So we can convert those multi-class discrete attributes into a set of binary attributes, right? So we're going to discuss about details later. And finally, we're going to introduce the concept of overfitting and explain why we do not like overfitting. Okay. So first, let us go back to the ID3 algorithm, the most classical and widely used decision tree learning algorithm. So as we emphasized, ID3 algorithm is a recursive algorithm, meaning that it will repeatedly call itself to grow the tree, right? Grow the new branches and split data sets and so on. Right? So whenever you design a recursive algorithm, the first thing you should think about is what is the base case, right? What is the, or in other words, what is the stopping condition, right? Because recursive, if you keep calling itself, and without appropriate stopping condition, it will just exhaust your stack of memory and make your system crash. Right? So in ID3 algorithm, what is the stopping condition? In other words, when should we stop growing the tree? Yeah, we got two stopping conditions, right? One is okay, if the current set of examples S they are uniquely labeled, right? There's only one label. That means, okay, they're 100% pure, right? There's no need to partition this data set anymore, right? This S anymore. So we should stop growing the tree. We should create a leaf node and assign the label, right? And the second case is also very important and is also common practice. That is, your attributes have been exhausted. It's possible that, okay, this labeling is so complicated, right? I just give you 5 features or 5 attributes won't be sufficient to let you reach a uniquely labeled set of examples, right? It's possible that you have used every attribute to split data set. You still have mixed labels, but in that case, you don't have other choice. You have to stop, right? Because you don't have any additional attribute to do the further split. In that case, I'm gonna return leaf node as well, and in this case, I'm gonna assign the most common label in S as the label for this leaf node, right? Just to make sure that you implemented correctly these 2 stopping conditions. Otherwise, you may see some kind of ghost bug. Some cases your algorithm works well, some cases just stuck there or even crash your system. Okay, and other than this, the 2 stopping conditions, we can consider how we grow the tree, right? So based upon the current set of examples, we're going to create a root node. Here, the root node means the global root node or the root node of a subtree, right? And then we're going to look at the attributes in the current attribute list, right? We're going to use some ranking mechanism, for example, the information gain, right? We're going to look up the best attribute A in ID3 algorithm. That means the one who has the largest information gain, right? And then we pick up the best attribute. Now we grow new branches according to A, right? So we're gonna go through every possible value V of that attribute A can take, right? For every particular value V, you're gonna add a new tree branch, right? And the edge of the branch is associated with testing condition, right? Test whether your A is value V, right? And if it happens that SV, meaning that examples take attribute A to be V, is empty. In other words, like there are not any examples in S that has attribute A to be V. In this case, we're going to add a leaf node, right? We're going to add a leaf node and assign the most common label in S as the label for the leaf node. Why? Why shall we do this? Yeah, let us recall the parallel shapes example, right? So it's possible that on some subset of examples, like triangles, right? Not triangles, like green shapes, right? The green shapes only have 2 shapes, like triangles and squares. It doesn't have circles, right? Sorry, my memory was wrong. Like it's only have circles and squares. It doesn't have triangles, right? If for the shape value triangle, you don't grow any branch and leaf node, what will happen? Well, what will happen? Yeah, you fill test case, right? So, for example, so this is a leaf node, right? So you might have like green, right? Forgive my bad drawing. And if you only grow 2 branches, one corresponds to, say, square, the shape type, right? The other corresponds to the circle, right? But you don't have triangles, right? But during the test case, what if I put you example, which is a green triangle? You know that, okay, starting from root node, I'm going to testing its color, which is green. Now I arrive here, right? But now you don't have any test branch, telling you, okay, which path you should go when you have a triangle shape, right? Then you're stuck there. You cannot provide any prediction. That's why when we implement our ID3 algorithm, to make sure that you won't have such kind of awkward situation, right? You need to create a leaf node, even there are no examples in S takes a particular feature value. And then here, in this case, for the green triangle, if I create a leaf node, I use the most common label in the subset corresponding to its parent node, right? And then I can give a prediction, right? So that's very important, right? It is to enable the generalization at test time, right? Please make sure to implement this detail. Yeah, that's here how we assign the label of the leaf node, right? And in this ID3 algorithm, we suggest you to use the most common label in S to assign label, right? So that means if your S contains all the green shapes, right? And you know that among those green shapes, there are no triangles, right? But you're going to still create a leaf node starting from this branch where the shape is triangle. And then your label is the most common label in the green shapes. Yeah, if there are ties, you can pick up arbitrary label. Yeah, you can specify more heuristic rules, like if there are ties, like for example, the most common label could be green, could be, I don't know, positive or negative, like because they have the same number of the examples, right? And you can say, okay, I like to prefer, in this case, I will assign positive label, right? But if you don't have any prior knowledge, you might just pick up random one. Yeah. It's up to the algorithm developer. There's no unique answer on that. Yeah, the problem is that, yeah, that's a good question. So the problem is that when you have such kind of cases, that indicates your data is sparse at some point, right? So you can only pick up the most trustable, most possible answer according to current data, right? If you have additional knowledge, well, as I said, like you have your additional knowledge telling you, okay, my preferences will be labeled plus, not negative, right? That's fine, right? But here, let's assume, okay, we only have the data set in our hand, right? And now you're gonna, from these limited sets of examples, you're gonna pick up the most reliable prediction. That's why we choose the most common, right? But again, if you have additional knowledge, of course, you can change the rule. Other question? Okay, yeah, just I want to emphasize this again, right? To make sure, like everyone, when you implement your ID3 algorithm, don't forget this detail, right? And if SV is not empty, that's good, right? I mean, at least a set of examples in S will take the particular value V in attribute A, then you can call ID3 again over this subset to consider further growing the tree or with leaf nodes in the subsequent steps, right? So, and this recursive calling, just to make sure that your attributes should kick out A, right? Why? Because A has already been used, right? In other words, look at this SV, right? All the examples in SV, their attribute A takes the same value V, right? So even if you preserve A, it won't give you any meaningful split. And then it just call itself and following the same kind of procedure and decide, okay, whether I'm going to grow in lymph nodes or further create new branches and call itself again until all the stopping conditions are met and the tree construction is done. Any questions so far? Okay, great. And hopefully our repeated emphasis on this algorithm can make everybody clear and feel easier to implement this algorithm and debug it. Right? Okay. So the last thing about this algorithm is how do we pick up the attribute A, right? We spent quite a lot of time in the last lecture talking about how to rank those attributes, right? So the idea is that we want to pick up an attribute that after using that attribute to split on data set, we're gonna maximally increase the label purity, right? Then the problem is that how do we measure the label purity? Right? And in the classical ID3 algorithm, we use the so-called information gain, which is based on the concept entropy, right? So entropy is a concept from information theory. It measures uncertainty about the labels in your data set, right? So high entropy means high uncertainty. And high uncertainty indicates a low purity. Right? For example, if you've got positive and negative examples, and if they're 50-50 split, then your entropy is highest. Why? Because you are most uncertain about whether which label it should be, right? It has the equal chance to be positive or be negative. So high uncertainty means high entropy and means low label purity. On the other hand, little uncertainty or low uncertainty means small entropy. Then it indicates a high label purity. For example, if I got 100 examples, right, and 99 are positive, right, only one example are negative. Right? Now, if someone asks you, okay, how do you feel the labels? How do you know the labels of this data set? I'm gonna say, okay, I'm very, very pretty much certain about that, right? I got little uncertainty about the labels because I know it's very likely to be positive. In that case, entropy is very low, right? And the label purity is quite high. Does it make sense? Right? So entropy reflects the purity, right? High entropy indicates a low label purity, and low entropy indicates high label purity. So want to measure that after you use an attribute split on the data set, what is improvement or increase of the label purity? We can calculate the decrease of the entropy, right? That's the idea. Right? That's how this information gain is defined. Right? I mean, if you feel like a little bit uncomfortable to catch the connection, that's totally fine. Yeah, because you have yet get used to that, but I have taught this class many times. So to me, it's quite like instant connection, right? But the whole logic is quite simple, right? You just remember, like, okay, high uncertainty means low label purity, low uncertainty means high label purity, right? And the increase of the label purity can be reflected by the decrease or reduction of the entropy or uncertainty. That's how we calculate information gain. Right? So definition is as follows. We're going to first compute the entropy of the entire data set. And then after you use A to split S, right, the data set S is going to split it into a list of subsets, right? And for each subset, you're going to compute the entropy, and you're doing a weighted average of them. Why we should do this weighted average proportional to the weight proportional to the size of the subsets? Because we want to account for different importance according to size, right? A size of a subset of examples of 100 size, of course, is more important than a subset of examples with only 10 examples, right? That's why we should do this weighted average. And then we just subtract the entropy of the entire set S by this weighted average. We get our decrease or reduction of the entropy, which reflects improvement of the purity. Okay, so and entropy is fairly easy to compute. Right? For binary labels, you just follow this formula, right? For multi-class labels, you just follow this form, right? And then, we got some concrete examples presented in the last lecture. We highly suggest you to manually construct those entropy, follow the lecture slides, so to give you a better sense of doing that. Then it will be much smoother for you to do the problem in the homework. Okay. Now let us talk about the variance of information gain. Right? So, as we mentioned, right, in the information gain, we use entropy to measure the purity of the labels in the split data sets, right? So, someone asked, right, is entropy the only choice? The answer is not, right? Actually, you can define a variety of metric for the label purity, right? So here we give two commonly used alternatives, right? The first example is called the majority error. So what's the majority error? Suppose we're not gonna grow the tree below, right? And we're gonna use the majority label of the current set of examples to predict every example, right? What is the error? So we can look at a concrete example, right? Suppose as some node, right, the associated data set has 15 positive and 5 negative examples. So now we're going to use the majority label. What's the majority label? Positive, right? I'm going to use this majority label as the prediction of all the 20 examples. What's the error? How many errors will we make? Yeah, 5 or 20, right? Because I use positive label as a prediction for the labels all the 20 examples. I know that, okay, for these 5 negative examples, there must be errors, right? So that test error will be just 5 over 20, which is 1/4, right? So what can we observe from the majority error? How does it connect to the label purity? Yes, right? The lower the majority error, the better purity. Why? Yes, right? So imagine that, okay, if I got 19 positive examples, 1 negative examples, what's the majority error? Is 1 over 20, right? So you can see that actually the smaller the majority error, the more pure of the labels, right? And of course, if all the examples are positive, like 20 positive, your majority error is simply 0. Right? On the other hand, the larger the majority error, the lower the label purity, right? So imagine like you get 10 positive examples, you got 10 negative examples, right? So the majority error is 1/2, right? So my question is, can majority error bigger than 0.5? No. Why? Yes. majority error, I mean, for the binary case, for the binary labels cannot exceed 50%, right? If it exceeds 50%, then the label you choose is not majority label, right? The majority label must take at least 50% of the examples, right? So majority error will be less than or equal to 50%, right? So you can see that in the most mixed example, meaning that you got the same proportion for positive and negative examples, the majority error is maximum, right? Okay, that means majority error takes a similar function. Can you use majority error to what? Yeah, for more than 2 labels, like 3 labels and 4 labels, of course, it can be bigger than 50%, right? But you can imagine, like, you can think about what is the upper bound of majority error for multi-class cases. Yeah, I will leave it as an exercise for you guys. Like, for example, if you have k classes, will majority error be bigger than, say, k minus 1 over k? I think about that. Right. But here we use this to we use binary cases to explain how does majority error reflect the label purity. Right. So you can see that it can also be viewed as a measurement of the label purity. It's kind of similar to entropy, right? The larger the majority error, the smaller the label purity. And on the other hand, the smaller the majority error, the better the purity. So if you want to measure like the purity improvement after using an attribute to split on data set, we can look at the reduction of the majority error as well. So then it naturally comes out this majority error gain. Right? So you can see that it's the same as information gain, except that I'm going to replace entropy in this formula by the majority error. And that's it. So you can even imagine that, okay, in your implementation of ID3 algorithm, if you're are like perfectionist, like you want your code to be super clean and looks super good, like you can define a abstract class called purity measurement class, right? And then this is your gain class or gain function, which you're gonna call your purity measurement and subtracted by the weighted average of purity measured over the subsets after you do this split, right? And then in your purity measurement class, you're going to implement different instances, right? You can implement entropy based, you can implement the majority error based, and you can implement other variants. Like, just give you some hint, like if you want to implement your ID3 algorithm, yeah, more generally. Okay, so in practice, another commonly used variant is called Gini index. Actually, Gini index in practice perhaps is even more popular than information gain. Okay. So what is the definition of Gini index? Right? If you're doing binary classification, Gini index is simply 1 minus the summation of square of p positive and p minus and p negative. And for the general multi-class classification problem, the Gini index is 1 subtracted by the summation of squares of every pk. Pk means the proportion of the labels of label k. Is it clear for everyone? The definition? What's p? It's a proportion. Like, for example, if you have 100 examples, 90 are positive, 10 are negative, then p positive is 90 over 100 is 0.9, right? And P negative, 10 over 100 is 0.1, right? And here for multi-class classification, PK is just the number of examples with label K over the total number of examples. Okay. So is this definition clear to everyone? So let us take a look at why Gini index can reflect the purity as well. So for convenience, let us just look at the binary case. Right? So when is Gini index maximum? What? Yeah, right. You can use a very simple inequality. You know that P plus squared plus P minus square is no less than 2 P plus times P minus. This the inequality we learned from high school, right? And because this is a minus sign in front of it, and then you're gonna upper bound it by this guy, right? And this inequality holds only when P plus equal to P minus, right? Which is 0.5 or 1/2, right? And when P plus and P minus are equal, you have a question? Yeah, are equal, both 0.5, we reach the maximum of the Gini index. But in this case, the label purity is the worst, right? Is the maximum mixed labels, right? So if we take a look on the other side, right? When is Gini index the smallest? You have all on one label. Yes, right? You either have all examples as positive or all examples negative, then your Gini index is 0, right? And just be aware, this guy is always non-negative. Why? Why? Yeah, the summation of all the proportion is 1, right? P plus P minus is 1, right? And remember, P plus P minus something between 0 and 1, right? If you take square of them, you're going to reduce their scale. So their summation must be less than 1, right? That's not equal to 1. Right? So that means this guy is always non-negative. And when one guy takes 1, the other guy must be 0, then your Gini index is down to 0, which is minimum. Right? And in that case, we know you got the highest label purity, right? P plus is 1, meaning that, okay, all the examples is positive, right? Or P minus is 1, meaning that all the examples are negative. Right? So now we can build up the connection. Right? The high Gini index meaning low purity, right? P plus and P minus are both 0.5. Your Gini index is maximum, but it's worst purity, right? Worst label purity. On the other hand, the smaller Gini index meaning higher purity, right? In the extreme case, like when Gini index is 0, you have the best label purity. All the examples have the same label. So you can see that Gini index serves as the same function as entropy and majority error, right? High Gini index indicates low purity, right? And low Gini index indicates high purity. Again, if we want to measure the improvement of the Gini index, improvement of purity, we can calculate the reduction of the Gini index. That's how we can get our Gini index gain. So you can see that it follows the same formula as the information gain. The only difference is that, okay, I'm going to replace entropy here by my Gini index. Any questions so far? There's no one answer on that. It depends on the applications. There's no guarantee like which one is better than the other. What I can tell is that usually Gini index is the most popular. People found that in practice is more robust than information gain. Okay? And majority error is even less popular than information gain. And majority error is more like a conceptual example to show you, okay, we can have a variety of definition or metrics to do that. Any other question? Okay, so next we're going to talk about how to handle missing feature values. Okay, so so far the ID3 algorithm assumes that okay, every example, their complete example, you have observed every attribute, right? You have observed the label, right? And of course you have to observe the label, otherwise it's not called supervised learning, right? So by practice, it's often the case that you will see some feature value missing. Like for example, yeah, we're playing tennis playing data set, right? I collected my activity on day 15, right? Unfortunately, I forgot to record the overload, right? But I know that, okay, the temperature is mild, humidity is high, wind is weak. I did stay at home. I did not go outside to play tennis, right? Now, how do we handle this new example with a missing feature value? Any thought? Yeah, that's an excellent idea, right? So we can try to complete this example, right? We can try to complete this example. Say we know outlook is missing, so we're gonna just complete it with the most common outlook value appearing in our data set. Right? Any other thought? Is there other approaches? Okay, yeah, that's a nice idea as well. Like, okay, let me summarize your idea. Okay, let us first build a decision tree on the data set, which consists of like all complete examples, right? Now, oh, the problem is that if you have this attribute missing, how do you make prediction? Right? Impute data. Mm-hmm. They use as a testing data. Yeah, that's one example. But for the testing data, you still need to tell the decision tree which value of outlook you're going to choose, right? Otherwise, you cannot use your decision tree. Any other thought? I mean, just give some random guess. Mm-hmm. The choose the ratio is same. Okay. Yeah, I think you're close to our ultimate solutions, but we're going to talk about that later, right? Any other question? Any others suggestion? So my understanding is that, okay, you're going to kick out this outlook feature on data set, and then you create decision tree, right? And then Okay, yeah, that's very interesting. That's very interesting. Yeah. Yeah, I guess that's feasible. I mean, you're gonna just like say if you have a no label, right? But you have to, I guess you have to enumerate over every leaf node, right? Which give the negative example, a negative label, and they go back and backtrack until they match all the remaining features, right? And you just count, well, whose outlook, who is the most outlook value, right? Yeah, that's definitely doable. Yeah. So okay, let us start with the like most intuitive solution first, right? Like, you start with high. Yes. Yeah. Yeah. That's a yeah. Um, but you can think about some like workarounds or that, right? Like you can ask that, okay, I must match every remaining feature value, or I just match part of them, right? I mean, if it happens that, okay, there are no path which matches all three feature values, they have to sidestep that issue, right? But again, this is a very smart idea, right? This is the first time I heard in my class, right? That's very good. So yeah, let us start with the most intuitive idea, like she just mentioned, right? So we try to complete the missing attribute. How can we do that? We can go over the entire data set, right? And pick up the most commonly outlook value showing up in the data set to fill it, right? And that's one way, right? A more refined approach is that, okay, I'm gonna look at the label of my incomplete example, right? The label is no, meaning I believe, okay, the outlook value should be consistent with negative examples. So just look at all the negative examples and which outlook value appears most frequently. I complete my outlook value with that value. Does it make sense? Okay. Now I want to introduce the third one. Right? This is like a pretty fancy technique, right? So because in those solutions, right? Even we consider like back starting from the lowest level and backtracking, we're always trying to like fill or complete or guess, impute the outlook value, right, with a single value, right? That might not be sufficient, right? Because if you make a wrong imputation, you're gonna lower the value of this example, right? So can we find a way that we consider all possible values that outlook can take? This is a third solution. It's called fractional examples. How can we do that, right? So we break this incomplete example into a set of fractional examples. Right? So remember, for the regular example, each example is counted as one example, right? But now, because I only have one single incomplete example, I'm gonna break it into three examples as well, but each example is just counted fraction. Right? And each example will complete or impute the output value with a different value, like sunny, overcast, and rain. And the fraction itself is determined by the proportion of the examples taking that particular outlook value. Say, in our data set, we got 14 examples, right? We got 14 integral examples, 5 of which are sunny, 4 of which are overcast, and 5 of which are raining. Then I'm gonna assign the fraction 5 over 14 as my count for the first example, which we assign outlook as sunny. Then I build another fractional example. I fill the outlook as overcast, right? And I assign the fraction to be 4 over 14. For the third one, I assign fraction as 5 over 14, but I impute the outlook to be rain. Does it make sense? Right. So in this way, like we're gonna try all possible cases, all possible outlook values in this incomplete example, right? And then the remaining question is that how do we add these 3 fractional examples into the original data set, and then to rank the attributes, say, well, information gain or Gini index and so on. Right? So let us look at an example, right? So this is my incomplete example, right? And to consider all possible cases that outlook can take, right? I'm gonna break it into 3 fractional examples, right? And the fraction itself is determined by the proportion of the corresponding outlook value you used to input across the entire data set, right? Which is 5 over 14 for the sunny choice, right? 4 over 14 for the overcast choice, and then 5 over 14 over rain choice, right? And they are all negative examples because the original incomplete examples is a negative example, right? So you can see that overall it doesn't change the total count of examples, because when you add up the fractions of the 3 examples, it will just give you 1. Right? Yeah. So overall, you're gonna have 15 examples, right? But I'm gonna break this single incomplete example into 3 complete yet fractional examples. What? The 15th one will be this one, right? But I'm not directly adding this one into this set. I'm gonna break this one into 3 fractional examples and add these 3 fractional examples into 14 examples. But in total, my count is still 15. Does it make sense? Right? So now let's see, like if we use outlook to split on the data set, what will happen, right? If we add these fractional examples, right? So we add one more example, this incomplete, as we mentioned, we're going to split it into 3 fractional examples, right? And we use outlook if we want to compute information gain of using outlook to split on data set, right? So that means we're going to add each of this fractional example into different subsets, right? So the first fractional example where the outlook takes sunny will be added into this sunny subset, right? The second one will be added into this overcast subset. And third one will be added into this rain subset, right? So previously, right, this is a previous partition results, right? For sunny subset, out of these 14 examples, we have 2 positive, 3 negative, right? Now we add a fractional example. The fraction is 5 over 14, which is negative, into that, right? Now, what's the total size of the subset? So previously, without this incomplete example, right, we got 5 sunny examples, right? Now, I add a negative example with fraction 5 over 14, right? So what's the size of the subset, sunny subset now? It's 5 plus 5, 14, 5 over 14, right? So what's the number of positive examples? It's still 2, right? The K is what is the number of negative examples? So previously we only have 3 negative examples, right? Now I add 5 or 14 negative example. So now the number of negative examples is 3 plus 5 over 14, right? So just a little bit cautious, right? Now the number of positive examples, number of negative examples could be non-integer numbers, right? But it doesn't matter. It doesn't matter how to compute the positive ratio and negative ratio and entropy, right? Right. So now we know that from this total 5 plus 5, 14 examples, 2 are positive, 3 plus 5 over 14 are negative, then P positive is just 2 over the total size, right? And P negative is 3 plus 5, 14 over the total size, which 5 plus 5 over 14, right? You got P plus, you got P minus, then you can compute the entropy for the Sonic subset. Does it make sense? Right? It's exactly the same computing procedure, right? The only difference is that, okay, you need to be careful when you add a fractional example into one subset, your total size is changed, right? And your corresponding positive examples, number of positive examples or negative examples will change as well, right? But you use the same way to compute the positive ratio, negative ratio, and use the exact same way to compute the entropy.
So what if like the missing entropy isn't like the retail, like at the very top? Should we still like use the entire training sample in order to like split up like the factors? Or should we just use like what subset or like right like
Okay, so think about that, right? So you got a missing, you got incomplete example with some missing attribute, right? So you'll notice that at the very beginning, you want to add them into the whole data set, then decide which attribute you're going to pick first to split, right? Which attribute pick up second to do the split, right? So that means at the beginning, it will be added into the whole data set and to decide which is the rule node. Right? Does it make sense? Yeah. Any other question? Yeah. Yeah. So imagine that this is the same as the normal ID3 algorithm. The only difference is that, okay, I'm gonna add several naughty examples, right? Each examples has some fractional count. That's it. Right? All the remaining procedure is the same. So you know, those examples can be involved in a series of splitting tree growing procedure. It's possible. Yes, yes, yes. This is telling you that, okay, we should first do this fractional examples breakdown, adding to the whole data set, and then run out 3. Yeah. No 5 example. You're gonna still have like 1 example in total, but imagine that I'm gonna break it into 3 examples, but each example just assign a fractional count, right? So like this one, right? So you got 5 over 14 example plus 4 over 14 example plus 5 over 14 example is in total still 1 example. Right? It's just like, okay, I'm not count as 1 single example. I'm just counted as a fractional example. Yeah, you should consider that, right? You know that most examples will be just counted as 1, right? But there could be some examples just counted as half or 0.3. And when you calculate size of the any list of examples, right, you have to add up their counts together. Other question? Okay, hopefully everyone's clear about that. So, and a final thing that I should be very careful is that when even after you compute entropy, remember we were doing the information gain or Gini index gain or majority error gain, right? You're going to do the weighted average of the entropy over every subset, right? And the weight is proportional to the size of the subsets, right? So now the size could be non-integer, right? We'll calculate that. Just be sure do not miss that. Otherwise, you might end up with weird results. That's our past experience. Okay. So now I will leave it as a problem for you, right? Think about that. Can you use the same procedure to compute the majority error? Can you use the same procedure to compute the Gini index? Actually follow the same way. Any questions so far? Okay, great. So now we have discussed the case that, okay, during the training set, you got some incomplete example, some attribute is missing, right? So what about in the test time? What about in the test time? I present you some example, but some attribute is missing. I still want you to give me some prediction. How can you do that? No, you don't know label. I want you to tell me the label by running your decision tree. Yeah. Any thought? Yes, excellent. Yeah, you're right. So let's start with the most straightforward one, right? We can still use the same strategy as we just discussed to impute the missing feature value first, right? And then I throw it in my decision tree, I get my label, right? But if we want to be more robust, right? Like what we have done in the fractional example, right? We can also do the same thing. Right? So for example, if I give you a test example, right? And I don't know the outlook value, right? So according to the distribution of outlook values in the training set, I can still break it into the fractional examples, right? So I break this test example into 3 fractional test examples, where each test example takes a different outlook value. And now I can throw each test example into my decision tree to get a prediction, right? So, and then according to fractions, I can count in total how many are predicted as positive, how many are predicted as negative. I pick up the one who has the larger count. For example, here, both the sunny, I mean, in both the cases, like if I impute outlook to be sunny and impute outlook as raining, I got positive prediction. And when I impute the outlook to be overcast, I got negative prediction. Then my count or my vote for the positive prediction will be 10 over 14, right? And my vote for the negative prediction is just 4 over 14. Then I'm going to pick up a positive prediction eventually. Does it make sense? Any question? Okay, great. Okay, so the third one I want to talk about is non-Bloom features. So in our previous discussion, we talked about, okay, if your attribute is continuous, right? It's real valued, we can use binning or use some thresholding to convert it into discrete features, right? But what if your discrete feature itself can have multiple values? For example, if your attribute is a brand, right? Brand, you might have 1,000 brands, right? And if you want to pick up brand to split on a data set, you're gonna grow 1,000 branches, right? Make your tree very, very large. That's not something we want. Right? Remember, our goal is to make the tree to be as small as possible. Right? So in that case, we can convert this multi-class feature to be a set of binary features. How can we do so? Right? Take the outlook as an example, right? We know that outlook can have 3 values: overcast, sunny, rain, right? So now I'm gonna convert the case that outlook is sunny as a binary feature, right? If sunny is true or not, right? If outlook is sunny or not, right? Or if outlook is overcast or not, or if outlook is rain or not, right? So you can see that if you got 3 possible values in your outlook feature, now you can convert outlook feature into 3 binary attributes, right? And if you got like 1,000 possible values in your feature, like run feature, right? You can convert it into 1,000 binary features, right? In this case, you kind of like, expand the number of features, but every time, because you're gonna only choose 1 binary feature, it can only grow 2 branches at a time, right? So it can largely reduce the tree size. Any question? Yeah, the tree size means that it is smaller in both width and the depth, right? So we're gonna still prefer, skinny tree, right, to the wider trees. What's your question? How to shrink tree? So let's for example, right? This is your some root or subtrees root, right? So if you choose some large cardinality attributes, right? So if you choose it, you can imagine that you're gonna grow a lot of branches, right? And each of them, maybe it's not all of them will end up with growing very deeply, right? But that might be a few nodes that you can further grow and further grow and further grow and further grow, right? So you can imagine the tree width is pretty large. Right? Now you convert it into a set of binary features, right? Then every time you're gonna only grow 2 branches. And if you can control the depth of the tree, the overall tree size will be small as well, right? So actually, when we talk about the practice of decision trees, you always do not want the tree to grow as deep as possible. That's why we would rather expand the list of attributes, so that to ensure the tree is skinny, and then I'm gonna control the depth of the tree to ensure the overall the tree is enough small. Can you draw a decision tree for what? For the Oh, okay. So, like for example, if you convert your outlook attribute to 3 binary features, right? So that means your 14 examples data set, you don't have outlook feature anymore. You have additional 3 attributes, binary attributes, right? So you can imagine at the beginning, you might pick up one of these 3 attributes as the best attribute. It might give you the best information gain. Then your tree will look like this, right? So this will be, okay, is sunny. This is not sunny. Okay. And then you got 2 subsets, right? One subset is like this one is sorry. This one is Sunny, right? This one is Sunny, right? You're gonna take out the binary attributes from your attribute list, and then just calculate information gain for the remaining features and pick up the one who has the largest information gain to further grow the tree, right? And this one is the set of examples who does not have the Sunny outlook, right? And then you're gonna compute entropy, you're gonna compute information gain for the remaining attributes. Maybe next time it will pick up a second binary feature value, right? Which is whether your outlook is overcast or not, right? And then this branch will be overcast, this one will be not overcast, and so on, right? And it actually can convert every categorical feature like humidity and wind into these binary features, and then your decision tree will be just the binary trees. Yeah, it is possible. That's what we expect. Yeah. There's no guarantee on that. Yeah. I understand your concern, right? So as we'll discuss later, right? So in practice, you want to avoid overfitting. So you don't want your trees to be grow like infinitely deep. You always set some threshold or set some strategy to stop growing the tree early. That's why, like, okay, you convert those categorical features into binary features, then you use some, so you make your tree skinny, and then you use some effective strategy to stop growing the tree too deeply. So overall, you will have a smaller tree. Yeah, we'll discuss about it. Yeah, that's actually is important in practice. But anyone, is everyone clear about this simple strategy? Mm-hmm. Yeah, there's a this is very flexible. Like we don't provide like once for all solution. It just give you some choice, right? Like for some cases, if your categorical features is too many, right? Cardinality is too large, and you don't want your tree to grow that wide, you're gonna convert it, right? For some cases, like for example, in this case, it's Sunny, right? Sunny only has 3 possible values. It may not be optimal to convert into binary features, right? It depends on the applications. Mm-hmm. Yeah, you should be done. You should done this before the running algorithm, right? So because we need to first convert them into the attribute, right? You need to first decide which attribute list you're going to use. Then you can run algorithm. You cannot at the intermediate step, your ID3, you're going to change your attribute list. That does make your algorithm continue. Mm-hmm. 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 Yeah. Again, there's no rules on that, right? If you decide to use Sunny feature, you're going to impute the Sunny feature and break them into fraction examples, right? And if you want to further, you can do that in 2 steps. Right? You can first break them into those features, and then you do the binarization of those features. That's fine, right? Or you can first do the binarization and then use the same fractional ideas to complete examples. It's flexible.
You still want that.
I didn't have a what?
You don't know what data set is in that.
Mhm.
So you still want that.
If you don't know if your test, okay, this is one comes from like test time, right? If you don't know if your test example is integral, there's no anything meeting, there's no point to use fraction count, right? Only it appears like, okay, you don't know some missing attribute, you want to impute them, you want to consider all the cases, right? To do that, right? And similarly, when you do the training, right? If all the training examples are integral, what's the point to add some fractional counts? Right? Another question? Mm-hmm. Mm-hmm. Yeah, it's if you convert it into binary features, you're doing the same thing, right? You if you take, okay, if you look at outlook, if I convert it into this binary feature, right? If I just look at all the examples, if you're gonna partition it in two sets, right? One set where all the outlooks is sunny, right? The other set, the outlook is not sunny, but it could be mixed, right? It could contain both overcast and rain examples, right? But it still have positive labels, negative labels, and you still can compute the period. It's nothing to do with the particular attributes it has, right? Other question? Yeah, you guys have a great passion about how to deal with this, yeah. But again, there's no a single rule telling you, okay, which strategy you use will give you the best performance. We just provide you as many options as you can, right? And the fractional examples appear to be more robust, but it still cannot tell you 100% sure that you use fractional examples will beat the other strategies. You just complete that with you just impute it with the most common label. That won't be that case, right? But everyone should know those choices. That's the key point. Okay, I think we can start. We can stop a little bit earlier today, right? So in the next lecture, we're going to talk about the details about overfit.